Yes, fine. So I'm sharing. Okay.
Yeah. Hi. Can I start? Hello. Hello.
Yes, Mohit, you can start.
Yeah. So my today's talk would be on. I'm going to present on artificial intelligence based techniques for scheduling in wireless networks.
And Dr. Mohit,
Next.
just to interrupt you,
Yeah.
I mean, can we take the questions in between?
Yeah, sure. No problem.
Yes, yes. So I request all the participants, if you have any questions, you can type in the chat box. So we'll immediately take up these questions.
Yeah.
Let us make it more interactive.
Yeah.
Yes, Dr. Mohit, please continue.
Yeah. Next slide. Next slide. Yeah, so the outline of the talk is that first I'll discuss basic building blocks of artificial intelligence and what actually the artificial intelligence is. And through this, I will actually try to understand, we will try to collectively understand that what is actually our goal. Then once we understand it and then we see that what are the basic building blocks of it, then we will look at some sample problems in wireless comm networks, that how to apply artificial intelligence to solve the problem in wireless networks. So, and then in the end, I'll leave you with some further readings. So let's start. Next slide. Yeah, so the first question which comes to our mind is that what is the quest for AI? So next slide. So basically the quest for AI is we want efficiency and we want to improve our lifestyle. Next slide, please. So in this, um, uh, we want to design certain type of autonomous agents which can actually do the routine type of work for us, and even the most complicated task which we hit which we may or may not want to do. So in the insert here, it is a headline which appeared during the COVID time, that which increased the sale of robotic vacuum cleaners. So they are a very simple form of artificial intelligence. So so the two key points, that we want better machines which have more efficiency and so which can improve our lifestyles. So now the question is, what is this intelligence? Next slide, please. What is this intelligence? How can we define the intelligence? So intelligence is just something which is the capacity for you to logic, understand, and self-awareness. Okay. Next slide, please. And how it is different from human intelligence. Basically, humans can not only understand and apply reason, they can solve problems, they can make decisions, um, and not only they can reason, they can change that knowledge which they have acquired through their years of experience. If they see that there are some opposite evidence, some counter evidences are emerging in the form of experiences. So basically, now the question is, is can you categorize the intelligence? Next slide, please. So we say that capacity to take decisions, to apply logic is called decision. Is called intelligence. So what is intelligence basically? So any form where you can actually gather some form of knowledge, and then you process it and take better decisions on it. For example, in athlete is an intelligent person. It means intelligence need not only be in the intellectual form. Okay, so for example, the body kinesthetic is a type of intelligence. Similarly, a good orator or a good writer is an intelligent person, right? So it can be linguistic also. It could be musical. You can design better music, or in the most common form, the intelligence is identified with logical and mathematical reasonings. Next slide, please. So and actually, next slide, please. So actually, in contemporary world, basically, all people are trying to mimic all type of intelligence, most of these type of intelligences. For example, people are trying to. Recently, there was a Robo World Cup happened in Japan, where the robots were trying to play volleyball with the Japan and US robotics teams were playing volleyball. I'm sorry, there might be. Is there some background noise? Are you guys hearing? And other form of intelligence is that it can help you with the existential issues. For example, recently the Apple Watch series was launched, which was able to capture the ECG on a person. Next slide, please. And or the AI can basically design a wide variety of music. And in fact, AI is also helping in proving the theorems and finding new planets. Next slide, please. So basically, so we can see that AI is in the coming days. AI is going to be a platform which is basically going to change multiple aspects of our life, and it is going to act as a platform, okay, on which many applications will be designed. Next slide, please. Now the question is, what kind of how can we acquire, how do we acquire the intelligence? Because we want to develop intelligence artificially, so we should actually know the process. So if you observe that in nature, humans or even any other living being, they actually learn through trial and error, right? So that's basically the process to that's basically the process to acquire the intelligence. So next slide, please. So if we want to just summarize that what is the way humans learning mechanism is organized. So you do some trial and error, those makes the form of experiences. Then you make some decisions based on those trial and error, and over time you keep refining those decisions. That is called training in context of machine learning. And you adapt these learnings to a new context. Whenever means you learn something in one context, and whenever there is a new context, you just modify those learnings, and that is called transfer learning. So for example, a very famous example I can give is invention of communication. So people saw that you can, for example, the people knew that the voice basically can be carried over the over the mechanical waves, right? Voice is a mechanical wave, and it can just carry it basically carries some disturbances which are basically created around your mouth, right, when you speak. So but the problem was that these disturbances, these mechanical disturbances or mechanical waves cannot travel too far. So what someone did, they actually did they imposed they converted those mechanical disturbances into the electrical form. And now you know that electrical waves can travel too far, and I just superimpose my disturbances on that electrical wave. That's called modulation. And basically what you are doing is you are doing the transfer of learning, right? So you need some experiences to learn, and you just train over those experiences, and whenever there is a new context, you just modify that learning. So that's basically the basically the protocol for learning for humans. So next slide, please. So even in neurological research, it has been proved that you can actually train your intelligence. It's not something which is associated with you, with your. It's not a congenital ability that which is basically assigned to you when you are born. You can actually improve your intelligence. You can become more intelligent over time, provided you put enough amount of efforts. Next slide, please. So now let's see that in practice how we can develop intelligence. So let's say we want to design a personal assistant, and similar to Alexa, let's say, to develop a personal assistant which can actually suggest clothing for the day based on the temperature at 9 a.m. Okay, so a possible design, basically the design requires that you input the temperature at 9 a.m. which your phone can capture through a sensor. And your personal assistant should just suggest based on 9 a.m. temperature whether you should carry a jacket or you should not carry a jacket today. So mathematically, I can think of it as a function, f assist, and the input to this function is temperature at 9 a.m. And the outputs of this function are my desired outputs: carry a jacket or don't carry a jacket. So, but this is a complicated function. I don't know that what is the form of this function. I cannot explicitly write it mathematically, but what I can do is I can somehow learn this function using my experiences. That is what humans do. They just collect enough experiences, and then based on those experiences, they learn this function. Next slide, please. Okay. And what helps in learning these functions is basically deep neural networks are universal function approximators. So basically, give me any function in the world, I can just approximate and give me enough neurons, enough number of neurons. I can approximate any function in the world using deep neural network. That's a very powerful property of deep neural networks. So I can approximate my f assist possibly using a deep neural network. So I just input in this deep neural network T9 AM and output will be those two outcomes which I need. Okay. So just to summarize, what is the learning mechanism for deep neural networks? I'll just give a brief summary of deep neural networks learning mechanism. Next slide, please. So what you do is you collect enough number of data in the form of tuples like T9 AM and output, desired output. Okay. And this is your set of experiences. This set of tuples, subset of these type of tuples is basically your set of these experiences, and you choose a loss function. So what you do is you excite this neural network using the input T9 AM and you observe the output and you compute the loss function, that how much I am away from my desired output. And based on this outcome, what you do is you just tune using some sort of a gradient descent. So basically stochastic gradient descent, which in the parlance of deep neural networks is called back propagation. So what you try to do is you try to back propagate the error from the output towards the input. So basically you try to tune these weights of these neural networks such that your function basically matches this data and it accurately captures the relationship between this data. Okay, so that's at a very high level. That is the learning procedure that DNNs follow to approximate a function. Okay, so next slide, please. Next slide, please. Yeah. So that's so we have we have captured one characteristics of the learning mechanism, that to approximate the functions. Another or decision making. So decision making was one of the characteristic of the intelligence. That's what we saw in the definition of intelligence. Another characteristic of intelligence is planning. So how do we plan basically? So usually at 9 o'clock in the morning, if I want to decide that whether I should carry a jacket for today or I should not carry a jacket, what I do is I just check the outside temperature, or if I just check that whether the sun is out or not, and then I do, based on my experience, I make some estimate whether this is going to rain or not, or it is going to be cold today or not. So basically we have some sort of probabilistic framework in, so this sort of estimation framework can actually be captured by some sort of probabilistic framework. Okay, so what we do is, let's say we define it as a Markov chain. So if it is hot today at T9 a.m., I just quantize the temperature into 3 states, let's say hot, cold, and rain. So if it is currently hot, there is a probability that with PHR it might be rain, or it might remain hot throughout the day with probability PHH, and it might get cold from hot by the evening with probability PHC, and the similar kind of probabilities can be defined in other states also. And based on these probabilistic framework, I want to take a decision, and my decision should be such that I minimize my penalties. And penalties are either I get drenched in the rain or I catch cold if I don't carry a jacket. And if I carry a jacket, let's say I don't have an option to put it anywhere else, I just keep sweating throughout the day. So my goal is I just want to minimize my penalty. Next slide, please. So to plan, basically what you do in just I'm summarizing what I said, that you plan to minimize the penalty, and you consider the current state and take into account the transition probabilities. Okay, so next state, please. Next slide, please. Yeah, so so basically this sort of decision making and planning framework has been captured in a mathematical construct called Markov decision processes. Okay, so the only assumption these Markov decision processes, as the name suggests, they have that these state transitions form a Markov chain. So by Markov chain, I mean that given the current state, the future transitions does not depend on the past. So if I am in a state hot, it does not matter whether previously it was cold or something else. The next state is always going to depend on the current temperature. It does not matter what was the temperature 2 days ago or what was the temperature yesterday. If I know that today's temperature, I can take my decision. So, and to describe an MDP, what you need is you just need to describe what are the all possible states. What are the actions you can take? The set A is set of all possible actions. That set S is set of all possible states. That what are the all possible outcomes which can happen? Okay, possible states are just set of possible outcomes. Action is set of all possible actions which you have to take, whether you want to take a jacket or not, don't want to take a jacket. And this T is a transition kernel or transition probability matrix, which tells you that if you are in a state S, and you take an action A, and then what is the probability that you transit to another state S? So this is very general. Basically, it is capturing the scenario when your action can actually affect the state S. So in wireless communications, we see this kind of scenarios. So in examples, we'll see this kind of scenario. And there is a function called R, which actually captures your reward or penalty. That if you take an action S, action A in state S, you get certain quantitative reward. Okay. And the goal is to basically maximize this long-term reward. So what the summation is basically denoting is that you want to maximize your long-term reward. And just for making it a little more practical, what you do is you don't equate all rewards. You don't weigh all your rewards equally. What you do is you weight your future rewards. That means you give less importance to future rewards, because this gamma is between 0 and 1. It's not exactly equal to 1. So what you do is you choose gamma such that how much importance you want to give to your future rewards. And this actually gives you a function which actually captures that how you want to compute your long-term reward. So that also the similar thing you also do in your life, right? What matters for you today may not matter to you tomorrow as much as it matters to you for today, or maybe 10 years later it may not be the same thing, right? So the goal here is basically to maximize the long-term reward, and basically how do we maximize the reward? By taking the action. So basically what I'm trying to say is that I'm trying to find a policy such that I take optimal actions which maximize my reward. And I want to find a policy which is a function from the state S, which take the state as an input, and it gives me an output as an action, and actions are chosen such that this reward is maximized. Okay, next slide please. Yeah, so basically this long-term reward in MDP means this is something which if you don't want to pay attention to, maybe you can just ignore this. Okay, just for sake of completeness I have included this slide. So the value function is nothing but, in the parlance of MDP, value function is nothing but your long-term reward. So what you want to do is you want to maximize this value function in any state, and your value functions, and there is a property called Bellman equation. There is an equation, famous equation in the control, which is called Bellman equation. And your value function, it is well known that your value function actually satisfies the Bellman equation. So what does the Bellman equation says? That your value function, that is your long-term reward from any state S, is the current reward, that the reward you get in the current state when you choose an action pi S, action according to policy pi, plus some discount factor gamma, and the statistical average of all future rewards. That is, this is the probability that you transit to state S prime when you take an action pi in the state, take action pi S according to policy pi in state S, and from there onward the value function or the long-term reward, you average all those rewards over all possible transitions, you get this all statistical reward, right? So there is a typo here, the bracket should be here. Okay, and what does the policy looks like? Policy is just choose the action which actually maximizes this value function. Okay, so usually there is a procedure called policy iteration or value iteration, which is used for this MDP solution. So I think we are not going to discuss that in this talk. So next slide, please. So now, based on this framework, I just want to introduce what is reinforcement learning. So reinforcement learning is basically the scenario when you don't know your probabilistic framework. You don't know how the transitions are going to happen, right? So just to bring back our previous example of personal assistant design. At the beginning, when you started learning everything from the scratch, you never know that what are the transition probabilities, right? You don't have a concrete framework for this. So what you do is you learn through trial and error. So reinforcement learning is actually a mechanism for learning through trial and error. So it is concerned with the learning in unknown environments. So by unknown, I mean that you don't know that your transition kernels. So what you do is you just define something similar to value function, which is your q, which is you call q function. Okay, and q function is quite similar to value function. It is just as that it is a two-dimensional function which takes into account both the state and action. And if you take an average of the q function, or if you take the expectation of the q function over all the over the distribution induced by the policy, you get the value function. Okay, and it follows that this q function also satisfies the Bellman equation. So the Bellman equation which I introduced on the last slide. Okay, so that means you can actually iteratively estimate this q function. So I'm directly jumping to this equation without any much background why this kind of iteration works, but just believe me that this kind of iteration actually works quite well, and it actually goes to the optimal point. Okay, so I will just elaborate on this equation. So what does this equation is trying to say is that your your Q function at the next state is as the Q function at the current state plus the reward you have taken, the reward you have achieved in this state ST for taking the action AT. And then what you do is you just take the difference between these two terms. So this is your max, the max over Q function at the next state minus this QTST. Okay, so if you rearrange this equation, basically you will get RST AT plus gamma this plus 1 minus alpha times QTST. So basically what you are doing, alpha times this thing plus 1 minus alpha QTST. So you are updating QTST with some weighted average. Okay, so this is basically, that's why alpha is called here learning rate. Okay, so we are going to refer back to this equation once again. So try to digest this equation. So next slide, please. Yeah, so what we try to do in deep Q learning is basically we try to mimic this learning procedure. So basically we try to approximate this Q function. Okay, we try to approximate this Q function using the neural network. Okay, but since there is a problem here that we don't have a priori data, like I mentioned that in DNNs you can train using data. So what we do is we generate a priori data using some target network. We design another network, and this network is just constructed by copying from the main network, which is my main network is my Q function. Okay, so I'm approximating my Q function using the main network, and I periodically I keep copying the weights of this network to another network, which is called target network, which actually generates data points for me, and not data points, target outputs. Okay, so it tells me what should be the output, because we don't know the output because we are learning through trial and error. Okay, so so that is what we do in the Q learning, deep Q learning. And why we do the deep Q learning? Because when let's say that in the real world there are large number of states and large number of actions. So as you saw that Q function is a two-dimensional function, and if you try to construct a tabular form, it would be quite unsuitable for large state spaces. And in deep Q learning, you can do better approximation and you can do it for large state spaces. And that is why you parameterize your Q function with some parameter theta, and that theta is this deep neural network. And what you try to do is you try to learn this theta through this deep neural network. And you try to and how do you generate the data points for this? Basically, output is generated by this target network, and rest of the input data is generated by your transitions, that is SAS prime. This is essentially capturing your transition dynamics, and R is reward here. So this is the first part of my talk, more or less. There is one more slide there after this, but I would like to stop here and see if there are any questions at this point. Are there any questions?
Is there any questions from the audience side? So one question has come. So from Vijay Selvan.
Yeah.
So how learning rate is calculated? Mohit, are you able to see this question?
Yeah, I'm able to see this question. Yeah, so learning rate is actually it's an empirical constant. Basically, you try to determine it through some trial and error. It's you cannot. It's difficult to tell beforehand that which one is what value will work best. So this is an empirical constant which needs to be determined through trial and error. But yeah, it's a very important parameter. It's a very important parameter, and and needs to be determined through trial and error.
Okay.
Yeah.
So if you have any other questions from the participants, please feel free to type the questions.
Okay. So let's wait for one more minute and
yeah,
then
let's wait for 1 minute. Yes.
Yeah, I think there is one more question. Yeah. So for
I am a beginner to AI course. So can you tell software used for deep learning? So what kind of softwares are used nowadays for deep learning works?
So basically, if you are familiar with Python, Python is the language for deep learning. Then the packages which are being used, I will type in maybe in this chat box for everyone. So you can use Keras. And Keras usually used with the TensorFlows, Keras with TensorFlow. Or you can use PyTorch. So these are two main packages out there, one by Facebook, one by Google, for doing the deep learning stuff.
Yes, Mohit. So which one is more preferable? I mean, can we use in diverse applications out of this three?
So basically, Keras is very simple one, and one can directly start working with Keras. When I started working with Keras. And TensorFlow is it requires too much of effort to put your basic simulation running. But Keras, because it comes with some ease, there is a cost one pays in terms of speed. So the speed is quite slow. While PyTorch actually balances both. So it is not as simple as Keras, but not as difficult as TensorFlow. But what happens is that it balances, and from research perspective, PyTorch is the one people prefer to use, and it has a better speed compared to Keras.
Yes. So PyTorch is the newest one, right?
Even they are updating the TensorFlow continuously.
TensorFlow, okay.
They both are getting updated continuously, but it has certain features like in terms of speed when you are training a large data set, for example, for reinforcement learning, right? What I observed is that Keras is quite slow compared to PyTorch.
Yes. Yes, thank you, Dr. Mohit, for your answer. So there is one more question from Dr. Sabita Vosale. So the question is, what are the challenges of using artificial intelligence in wireless network?
Yeah, so basically
how feasible?
That's the second part of our talk, that what kind of challenges we see here. But on a high level, one is that a couple of challenges I can tell at a very high level. One is that we don't have these reward function and these transition probabilities already available. One is the modeling part, right? And not all wireless problems can be directly modeled into a deep learning problem. There might be some some wireless problems which actually don't fit, right? It's a tool. Artificial intelligence is a tool. So your problem may not be suitable for that tool, or it might be quite suitable. So one is the modeling. Another is that explainability. Because you are doing something using data, you don't know what kind of outcome it is going to come. So you cannot explain wireless communication system conventionally has been designed based on theory, and you have perfect explainability for them in mathematical terms. Like you have a capacity expression for each channel, almost most of the channels in wireless network. You can tell that if I transmit at this rate with 99.999% probability, I'll be successful if the rate is below capacity. But in AI case, what happens is there is certain form of randomization going on because of stochastic gradient descent. So the explainability, modeling, these are the two challenges at very high level I can think of. But there are other challenges, some of them which we will discuss in this talk.
Yes, thank you, Dr. Mohit. There are a couple of questions. One from Vijay Selvan. The question is actually, what is the real meaning of deep? In the sense, more parameter estimation or methods used?
So the deep means, if we go back to our neural architecture of our neural network, right? You can arrange these neurons in two ways. Either you can make it more deep, that means in a horizontal direction, or you can make them tall. Okay. So what
Shall I
works
show
best?
you some network on your slide, or explain this?
That would be a bit more convenient.
Yeah.
Yeah. So in this network, either I can arrange these neurons in the horizontal direction, or I can stack them in the vertical direction, right? I can have fewer layers, but a tall network, or I can have more number of layers, but very not so wide layers, right? So basically, through trial and error, people have observed that that this sort of arrangement, such that less wide layers but more number of layers, actually works well. There is a reason for behind it, but it's not fully understood yet. So that is what the deep is. Deep means that there are more number of layers.
Yes, thank you, Dr. Mohit. Let me show you the question platform. So we answered. Okay, the next question is from Susmita. So how the weights are initialized in a network?
So there are number of methods for initializing the bits. I can so at a very high level, I would say, rather than giving the specific name, all the bits are initialized in the randomized way. So you just choose Gaussian Gaussian distribution for initializing the network of the initial weights of the network.
Yes, thank you. So the next question is from Poli Anand. So basically, it's question regarding application of deep learning in channel estimation in wireless networks procedure. So how to apply deep learning techniques for channel estimation in wireless networks? I guess there are many works in literature. Mohit, maybe if you are comfortable, you can comment on this.
How AI can be used in physical layer, and okay, this one for channel estimation and wireless
channel estimation, yes.
AI,
yeah,
best
the last
procedure.
question.
So see, there are it's a very general question, because the best can be quite qualitative, right? How do you define the best? So but all deep learning based or AI based developments for wireless networks follows the same principle, which I have summarized in my previous slides, that you have a function which you want to map through deep neural networks. That's it. So now, how do you specifically design the network, and what kind of training you want to use? What is the network architecture you are going to use? That you have to find out through trial and error. And for channel estimation, there are some bunch of studies. In some, I have seen people are using CNNs. In some, people are using feed forward neural networks. But because they do not use a common metric for comparison, so it will be very hard to say which one is best. So it depends that what is the best is defined with respective to.
Yes. So thank you, Dr. Mohit, for the answers. And I think it's a valid question for channel estimation in wireless networks. So I guess channel estimation will require some kind of AI techniques in future.
Yes.
So yes. So if there are no further questions, so shall we move to one more question? Oh, okay, okay.
Yeah.
So, question from Kannan. Can you little more elaborate on how AI can be used in physical layer in next generation wireless network?
Yeah. So in the next part of talk, we are going to elaborate on it.
Yes.
Yeah. So let's
then maybe let's move to the slide, right? Fine.
So next slide, please. So these are some bunch of variants of RL. There are model based, model free. There is model free can further be classified on policy, off policy. And then there are other variants, policy gradient, act architect. So I'm not going into the details of this. But I think at the bottom of the slide, I have given a reference here. Maybe you can look at it. And in the end also, I'll provide some references. So the key takeaways for this, next slide, please. Next slide. Next slide, please. So just to summarize the key takeaways for this talk, as I said, that DNNs are the universal function approximators. And given you just in any wireless problem, you just have to identify that what is the function you want to mimic, and you want to just collect enough data for that function which accurately represents that function, and you just train your DNN for that function, and that's it. Now, although I will just give a disclaimer that simple training of DNN is not the artificial intelligence. The closest form of artificial intelligence is reinforcement learning, or what we are calling it as deep Q learning is one example of it. Okay, so in the next part of in the remaining of this talk, I will just discuss some examples of use of artificial intelligence techniques for wireless network. So next slide, please. Yeah, so this is in this part of the talk, I am going to discuss about a communication system where these rewards are sparse. So it's not only using the artificial intelligence or reinforcement learning for designing, for optimizing a communication system. What it is going to do is that the system itself is plagued with some problems. So let's see what are these problems. So this problem is a sparse reward problem. So let's see in this part how this problem actually affects and how do we solve it. Next slide, please. Yeah, so let's just recapture what the RL is. RL is that you have a system which is basically being represented by your transition kernel, this function TSAS prime, and you have RL based controller. It takes an action A, and that action A goes inside this kernel, and it determines your transition to the next state, and you get some reward. And those state transitions, that is the next state, and the reward is fed back to this RL controller. Okay. So now what happens is that basically, if you might recall from the deep Q learning slide that this RL agent actually learns using experiences. It actually reinforcement learning mimics our learning, humans learning procedure, right? What it does is it collects the experiences in this form, in the tuples of this form, RS AS prime, right? So that is all you get to observe about the system. The current state, the action you take, and the transition it induces to the next state, and the reward you obtain for that. That is all you observe, right? And that is why it is called experience. So when you take an action, you just observe these three things, and this forms your experiences. So the collection of this form of tuples is called experience. Okay. So now, what happens is, since you learn through experiences, and if there is a sparsity in the reward, what do I mean by sparsity is that if the reward is 0 for most of your actions, and for most of these tuples have the reward 0, that means your system will not be able to distinguish between what is the better action, what is the bad action, what is the good action, what is the better action. So you will not be able to quantify your actions, and the reward is basically a feedback for your actions, right? So if you get most of the time you get a 0 feedback for all of your actions, you don't know, it becomes very difficult to learn. So that is the problem, right? So it makes reinforcement learning quite challenging in this scenario. So that's at a very high level. That is the crux of this talk, and let's take a specific problem and let's try to solve it. Next slide, please. Yeah, so in this for this purpose, let's consider a system model which is as follows. You have a controller which actually have to decide for input data packets that to which queue one data packet goes to, and what should be the rates of these service rate of these queues. Okay, that means at what rate these the data in these queues should be served over their channel. So these queues are being served over bunch of parallel independent channels, or they can be temporally correlated, even spatially correlated. Okay, we don't care about it, but there are some parallel channels. Okay, and over these parallel channels, the data from these queues is being transmitted to a receiver, and your goal is to basically minimize the minimize the delay in the processing of this data. So queuing delay you want to minimize. So what do I mean by queuing delay is the time difference between the instant you get inside the queue and the instant a packet gets outside the queue. So the time a packet actually spends in a queue is called queuing delay. So we want to just minimize that queuing delay. So this is quite useful for the problems which require ultra low latency kind of characteristics. Next slide, please. Yeah, so just to summarize, what is the system model? You have a point-to-point communication link, and data packets arrive at the transmitter with random inter-arrival time and size. Their size is also random, and both of these random distributions are unknown to the designer. Okay, and there are k queues which are served over k parallel channels in a first in first out fashion, and a data packet is dropped if it is not served within capital T slots from its time of arrival. So we have a deadline by which the packet should be served. If it is not served by that deadline, we just drop it because it's useless. And that is basically in line with the ultra low latency type of applications. And here we denote the feeding channel gain for the kth queue and the receiver in the nth slot with HNK. And the joint distribution of these all k channels is basically an unknown distribution, and the goal here is to learn an optimal policy to update the service rate of these queues and schedule the packets to these queues such that this packet drop rate is minimized. And the assumption here is that data packets arrive at a slower time scale compared to channel coherence time. So this assumption is just for explanation purpose. It has nothing to do with the final solution. You can assume other way around, or you can assume the same time scale also. Okay, if there is a same time scale, then this sparsity problem will go away. But if there is a difference in the time scale of the data packet arrival and the channel coherence time, this sparsity problem will arise. So I'll illustrate it through an example. Let's just move to the next slide. Yeah, so mathematically I can write this problem as this. Next slide, please. Basically what I do is I just try to sum all the indicator functions over all the queues. This indicator function is just denoting that if the head of the line packet of the kth queue is being dropped in the nth slot or not. I sum it over all the queues, so that inner summation gives me the total packet drops in a given slot n across all the queues, and then I sum all the drops over all n slots, and then I take time average of it. Okay, and we want to minimize this over this pi. It means we want to find a policy which minimizes this quantity, and just ignore this lim sub thing. It's just a mathematical technicality. So the policy basically has to determine these indicator functions, which is basically the assignment indicator functions for queues and these rates. Okay, so these indicator functions. So let's say indicator function with subscript n and superscript 1 denotes whether the packet in the nth slot arrived in the nth slot is assigned to the first queue or not. Okay, if it is assigned, this indicator function takes value 1, otherwise it takes value 0. And these rates are basically service rates of all the queues in the nth slot. Next slide, please. Yeah, so that's it. This is all just I have described. Next slide, please. And these RKNs are basically assigned such that a given rate RM is assigned to only one queue, and these queues evolves in a Markovian fashion. Okay, so basically, Kuntal, the bottom part of the slide is not appearing in the full. Can you? Yeah. So yeah, thanks. So basically, what you do is that these queues are basically evolving in the Markovian fashion. That is, the queue in the next slot is basically the queue length in the current slot. The subscript k is denoting that it is kth queue, plus the data arrived in the current slot, minus the data or the removing the data from which has been processed in the current slot. And this max is basically taking care that if the queue is empty, nothing gets processed. Next slide, please. Yeah, so ideally this problem is a basically sequential decision problem, and in principle we can model it as a Markov decision process. And what happens is difference in these time scales of channel coherence time and data arrival process leads to sparse rewards. So let's see what is this sparse reward problem. Next slide, please. So let's consider an example. So for example, let's say the channel coherence time is 5 milliseconds. So my slot duration is 5 milliseconds. And that means my channel remains constant for 5 milliseconds. And on an average processing time, let's say for my packet is 300 milliseconds. So on an average for a packet policy with 10% drop rate, a non-zero reward is obtained approximately every 600 slots. So by non-zero reward, I mean I get a penalty whenever my packet is dropped. So every 10 packet, every out of every 10 packets, only one packet get dropped. Okay, and since my packet coherence time is 5 milliseconds, so and packet processing time on an average is 300 milliseconds. I'm going to take 60 slots for processing a packet. And to observe my 10 packets, I will need 600 slots. So out of the collected 600 experiences, so I collect experience in every slot. Out of collected 600 experiences, I'll have a non-zero experience only in one slot. So that is the sparsity in the reward. And when only one sample out of your 600 samples is useful in learning, then it actually increases the sample complexity exponentially. That means you require an enormously large amount of data for learning the desired behavior for your system. Next slide, please. Yeah, so this sparsity of the reward function actually leads to exponential sample complexity. Next slide, please. So as a consequence, what happens is that the conventional deep queue learning basically performs quite poorly. So what we do in this is we use a technique proposed in this paper called prioritized experience replay, and we try to modify this double deep queue learning RL, and we see how the system behaves. So in the remaining talk, I will basically describe that solution, just that solution. What is this prioritized experience replay? Next slide, please. Yeah, so as we know now, I have repeated several times that RL learns using experience gleaned through interactions with the environment. And what this prioritized experience replay does is that it prioritizes the samples used for learning based on the informational value for learning. So what do I mean by prioritize is that you store all these samples in a buffer, okay, and you randomly in the conventional deep queue learning, you randomly sample that buffer. So you randomly choose a batch of samples from that buffer and you train your deep neural network on that. But when you want to prioritize it, what you do is you give priority to certain samples. You choose them again and again. You choose them more frequently, or you choose the likelihood of a selection of those samples for training is more. So what I do is I set my likelihood of the selection of the sample based on the information, their informational value for learning, and the informational value of their learning is basically based on this thing delta n. Okay, so if you remember the basic equation, if you can recall the basic equation for Q learning which I described, it is in the same form, right? R plus gamma times Qn minus Qsn1 minus n1. Okay. So here this Q is basically Q function. So based on this delta n, what I'm trying to do is I'm trying to define some prioritization. So the prioritization can be this Pi is the probability of priority, that how much priority I give, denoting the priority. So Pi, if I can define a proportional prioritization. If I define my Pi to be the delta I plus epsilon, or I can do, this is not probability, I'll define probability using this prioritization parameter. So, and there could be a rank based prioritization. I can define this Pi priority as a 1 by, in the inverse relation as a rank of ith sample, or this I is the priority. Next slide, please. Yeah, so using these priorities, I define a distribution over these samples with probability capital Pi, and here alpha P is a positive constant chosen to be positive, such that you don't you end up with a valid distribution. Means you don't end up with a uniform distribution like before. If you set this alpha p2 equal to 0, you end up with a uniform distribution like before. And you, if you set alpha p equal to 0 in this algorithm, you go back to the original deep Q learning. And since you are not equally likely sampling sampling from your buffer. Since you are sampling with some sort of distribution, so what happened is that you introduce some bias in this estimation of this parameter theta of your neural network, right? So to correct this bias, this is some technical details. I'll just go through it. Just ignore this. But basically, at high level, to correct this bias, what you do is this bias is being introduced due to some prioritization. What you do is you define a weight which is inverse proportional to the prioritization. So that the change in the Q function, or the gradient of that gradient for that particular sample corresponding to that particular sample is basically weighted with a smaller quantity. Okay, if that is very large. So since you are going to update this more frequently, you are going to use this gradient term more frequently. What you do is you multiply it with a weight which is basically smaller in proportion to your prioritization thing. That is what it is at high level. So basically what you do is you correct the bias which is introduced through sampling by using some sort of importance sampling. Okay, next slide, please. Yeah, so just to summarize this entire prioritized experience replay, there are two key steps. One is you prioritized based on your informational value in the sampling. That means how much important my sample is in the learning. Okay, and then since this type of prioritization introduces some sort of bias, I just do some stochastic sampling. That is the prioritized experience replay in a nutshell. Next slide, please. So now we try to see that how does this algorithm performs for our problem. So just to benchmark our problem, we use first some shortest processing time agent. That means an agent which actually computes your assignment to the queue based on the queue length. Okay, and if you keep the rates constant throughout the operation, you don't update the rates, you don't vary the rate across the operation. You just compute the only part of the policy which you are controlling here is the assignment of the packet to the queues, and the assignment you decide based on the queue length divided by the service rate. So how much time it is going to take to process the arriving packet. So you assign your packet to the queue which is going to take the shortest time for processing this queue. So what I do in this simulation is we plot average instantaneous packet drop probability as a function of time, that is as the number of packets scheduled increase, for 3 different tuples of the rate, that is 1.6, 4.3. So we fix the total rate to be 5.3, not 5.3, 2.4, 1.9, 3.4, 4.3, 5.9. Okay, so we fix the total rate to be 5.9, and we have to split the entire rate between two queues. Okay, so this is my 3 modulation and coding schemes available, and I have to assign these modulation and coding schemes across the queues. Okay, and I can have 3 possible combinations, and I analyze those. Means there can be many other possible combinations, but what I do is I just analyze these 3, and what I observe is that out of these 3, 2.4 and 3.5 actually performs best. That is the equal kind of rate assignment across 2 queues. Here K is capital K is 2. That is the total. There are only 2 queues. So across 2 queues, the equal kind of rate assignments, the symmetric rate assignment works best. Okay. So just to be sure, just to ensure you that other rate assignments which are not plotted here also perform similar. So this 2.4 and 3.5 is the best. So now this is going to serve as my lower bound. Okay, which is basically what I observe in this plot is this PT equal to 0. This golden curve is 2.4 and 3.5, and this is my lower bound when I set my transmit power to be equal to 0. That means to compute the lower bound, what I do is I say that at whatever transmit power means whatever the rate I assign to my channel, it just goes through. Okay, it just goes through. That means the received SNR should be 0. Okay, I can decode even at the received SNR being 0. So what I see is that there is a gap between this lower bound and the best performing SPT scheme, this golden curve and this purple or blue curve. And I can improve this if I can do more intelligent rate allocation. So in the next we do this try to do this rate allocation using reinforcement learning. Next slide, please. Yeah, so this is the summary of the things I said, that rate allocation 2.4 and 3.5 achieve the best performance, and there is approximately 7% gap in this performance, so which we try to attain through reinforcement learning. Next slide, please. Yeah, so there are 3 plots in this. Here again we are plotting average instantaneous packet drop probability with the number of packets as time evolves in the system. So this is how the learning dynamics of these 2 algorithms look like. One is deep double Q learning, which is this dark red curve, and another is orange curve. So if you zoom it a little bit, what you observe here is that this orange curve is most of, like 99% of the time, it is 3 to 5% below this double deep Q learning or this shortest processing time agent's performance. So it actually reduces the packet drop probability by around 5%. So in a ultra reliable and low latency type of communication, if you can improve the reliability by 5%, that's actually quite a good improvement. Next slide, please. Yeah, so in summary, we can say that DDQN basically performs. So the conventional Q learning was actually performing worse compared to even SPT. You can see these high peaks. And this DDQN PER actually outperforms both the DDQN and shorter processing time by up to 5%. Next slide, please. Yeah, just to summarize, we illustrated the impact of reward sparsity on the performance of RL. And we developed a prioritized experience replay based RL scheme for online learning of optimal cross-layer scheduling policy. And then we proposed policies which achieve packet drop rate close to the lower bound. And we proposed PER based RL scheme, which is useful, which could be useful for multiple scenarios where there are multiple random processes involved with different time scales. Yeah, so that's the second part of my talk. And before going to the last part, maybe we can take a short pause here for questions from this part or from the previous part. Are there any questions?
Yes, let's wait for 1 minute.
Yeah, because time is busy.
Yes. one question is there. So in wireless communication problems, AI is expected to excel in terms of better performance, or complexity is a bottleneck. Could you please comment on the complexity that is involved in integrating AI techniques in solutions to wireless communication problems? So Mohit, are you able to see this question?
Yeah.
Yes.
That is involved in integrating AI technique. So I'm afraid that I will not be able to give you a perfect answer for this, because use of AI in wireless communication systems is still in very infancy stage, and we are just at the beginning of this entire thing. But what we are observing here is that we are observing improved performances when we apply AI. So and in terms of complexity, your complexity, for example, in simple neural network, but let's say if you do the training of your RL offline, that means you train your network offline and then you deploy it on your node. That means you don't do any further training after deployment. So the neural network is not going to be consume too much energy. It's simple addition and multiplication, right? But if you do the training, so on nodes, basically on a wireless communication node or in hardware, basically the energy is consumed in these energy in memory fetching operations. So when you do this this type of training on board on a wireless node, you consume a lot of energy in this memory fetching, like you are fetching the samples, you are randomly sampling, and then you train them, then again write those. So those memory operations consume most of operations. So if you don't do the training on board, then it's not going to be complex. But if you are going to do the training on board, it's certainly going to consume a lot more energy.
Yes, thank you, Mohit. Is there any other questions? Yes, one question from Kannan. So is it possible to use AI in selection of channel coding?
I'm not sure what do you mean to say by selection of channel coding, because channel code is always fixed at the start of operation of any wireless comm system. If you are asking that how do we do selection of modulation and channel adaptive modulation and coding using AI, I think this is what I described in my previous part of my talk, where we were doing the rate adaptation across the slots.
Yes, Kannan, if you are there in the meeting, I mean, you can unmute and further explain the question.
Yes, sir. Yeah. Actually, whatever I like to know, if using some training sequence, you can predict the channel coding. Say, for example, a simple channel coding for certain part of the communication, and after that we can go for based on the channel. The channel estimation can be automated. Not right now. We are expecting that AI will help to make the channel prediction automated. Similarly, that aspects can be bring to this channel coding or modulation technique.
Yeah. So you are talking about adaptive modulation coding, basically rate variations, right?
Yes, sir. Adaptive modulation based on this channel estimation.
Yeah.
Both automated.
Yeah. So that is what I described in the previous part of my talk when I am adapting the rates across the queues, right?
Okay, sir.
Yeah.
Yes, that's a very good question. So, I mean, depending on the channel quality, I mean, the rate will be, I mean, rate can be made adaptive.
Yeah.
Yes.
So
also the channel estimation also can be done through AI.
Yes.
So both the tasks can be combined.
One can use reinforcement learning to just do the future channel prediction and automate that process also. So the next question is how do we find unknown distribution from data? So you don't need to find, if you are using RL, you don't need to find the unknown distribution from data samples. That's the beauty of RL, that you don't need to know anything about the system. You just run your RL in the system. It automatically tries to learn the unknown aspects of your system. You just need to define the suitable reward function and and choose an appropriate learning rate, you should be doing fine. Yeah. Any other questions?
Yes.
Yeah. If not, then let's
move back to slide.
Yeah. So
right.
yeah. I wanted to ask that check that how much time I have so that I can appropriately pace it the last part of the talk.
Yeah, typically, I mean, the schedule was for 1.5 hours. So you started at around 11:15, maybe 12:45 up to 1 p.m. we can extend.
Yeah, so let's try to finish it in 15 minutes.
Yes. Thanks. So one more question just came up. So AI from Shubham, can AI be implemented in UAV drone communication?
Yeah. So that's quite possible because we did not qualify that the previous system is for drone or for base station or anything. So you can deploy the same system which we described in previous part of the talk. We discussed in the previous part of the talk. We can just use it in UAV also. And actually there are a bunch of papers on UAV and reinforcement learning.
Yes. So since Mohit, you are in Singapore, let me give you the exact time. I mean, you have around 25 minutes, 20 to 25 minutes.
Yeah, it's okay. It's okay. We can finish in 20 minutes. I think
yes.
Yeah, so in the next part of the talk, I want to give you a flavor of distributed AI, that is through the multi-user communication system. Okay, so in this part, what I would try to do is that you don't even have the complete information available at each node about the entire system, and you are trying to learn the behavior in the distributed way. That is the problem here we are trying to deal with. So next slide, please. So in this context, we will discuss the energy harvesting systems. And so let me just briefly introduce what is energy harvesting and what are the constraints for energy harvesting systems. So basically you have energy harvesting nodes which actually harvest energy from the environment. It could be either solar or it could be through vibrations or kinetics, any kind of energy source. And these energy harvesting nodes are typically equipped with finite size batteries. And they operate under energy neutrality constraint, which is basically the law of energy conservation, basic law of energy conservation, which we study in 11th physics, right? So what it says is that at any point in time, your total energy consumed cannot exceed the total energy harvested. Okay, so this LHS is the total energy consumed and RHS is basically total energy harvested. And your concern here is that you want to design this energy consumption pattern in such a fashion that these constraints are not violated. So basically this constraint has to be satisfied at any point in time. So if you have total capital N slots, you have capital N constraints in this problem. Okay, so this is a control problem. You want to control the system in such a way that this constraint is satisfied always. You never want to draw energy from the battery. Means when it is empty, means you cannot draw, right? So generally what makes this problem more challenging is that these energy arrivals are random. So you don't know that whether the more energy is going to arrive in the future or not. So because of this random nature of these energy arrivals, so this RHS side of the summation is random. So you have to design these power consumption patterns PNs to satisfy these constraints even when the RHS is random. What is the last point? Can you? Yeah, so this problem is actually quite intractable for large energy harvesting networks. Even if you formulate as an MDP or try to solve it in a centralized fashion, it becomes quite intractable. Next slide, please. So the system model here is that we are considering a MAC network, multiple access network with the energy constituted by energy harvesting nodes, which are having a finite energy, finite size battery to store the energy. And they transmit over some wireless channel, and they have their individual harvesting processes, and these nodes do not communicate with each other. They do not know what the other node is doing. And next slide, please. Yeah, so the system model, just to summarize, is there are k identical energy harvesting nodes, and they harvest energy according to an unknown process, but it is a stationary distribution process. So they don't even know that what is the distribution of their own energy harvesting process, and they have to satisfy this energy neutrality constraint. That means that at any point in time, that their power consumption cannot exceed the maximum power transmit power allowed by the system, or whatever is available in the battery. And the battery evolves in a typical Markovian fashion. This min is basically that you do not overflow the battery capacity, and this plus in this entire inner summation is in this over this square bracket is basically max over 0. So you are saying that you do not deplete the battery after the battery does not have any energy. You do not try to pull the energy out of it, and it's a typical Markovian fashion as I described for Qs. The energy in the battery in the current slot plus energy arrived in the current slot minus the energy consumed in the current slot. Okay. And G and K, as we saw in the last slide, is the feeding channel gain, and they are also distributed according to some unknown stationary distribution. Next slide, please. Yeah, so to mathematically write this problem, what I say is that in nth slot, the rate achieved is this log 1 plus sum over SNR of all the nodes, and then you take, so this inner log is basically representing the total number of bits achieved in the nth slot, and you sum all the bits over the entire time horizon, and you take time average of it. You want to maximize this time averaged throughput, and subject to the constraint that subject to energy neutrality constraint. Next slide, please. And these constraints apply for all times and for all the nodes. Okay, and the maximization is here happening over these the variables you can control are these transmit power levels which you can control. Okay, next slide, please. And more importantly, the goal here is that since these nodes cannot communicate with each other and they do not have any information about other nodes, that whether they have the energy in their battery, what is the channel state of these nodes, they have to learn this optimal behavior in a completely distributed fashion. They don't know anything. They don't know their distribution. They don't know what other nodes are doing. They don't know their distribution of their channel. They don't know the distribution of their energy harvesting process. All they can do is they can just control their transmit power level, and they are truly interacting with the system and trying to learn the optimal behavior. This is like self-organizing system. So next slide, please. Okay, so to be precise, what the kth node knows, it only knows its current state and the history of its own state. So what is the state? Energy arrived in the current slot, and how much is the energy in its battery, and the channel state. Next slide, please. And the previous values of these things. So just to show you, so first consider this problem, that this problem is basically is as follows. Let's say you have bunch of you want to set up a wireless sensor network, and you have bunch of energy harvesting nodes, and what you do is you just throw them in some unknown environment, and these nodes in unknown environment just try to figure out their optimal behavior. Now let me say, even if you solving this problem in a distributed fashion is a non-trivial problem. So that is what I am trying to show through this example, that it is non-trivial even if you know energy arrival of all the nodes. So let's consider a scenario when there are 2 nodes and there are only 2 slots. You have to transmit only over 2 slots, and there is total energy of 5 units each node can harvest, and that entire energy arrives at the start of the operation, and they know the value of this total energy arrival, and they know only their own channel state in both the slots. Okay, next slide, please. So let's say in time slot 1 and time slot 2, these are the channel values for both the nodes. Node 1, the channel value is 2 in the time slot 1, and time slot 2 also it is channel value 2. Channel gain value is 2. Now for node 2, the channel in the first slot is bad. For node 2, the channel in second slot is quite good. So now what is the some throughput? Let's say had these nodes not known these channel values of other nodes, but only their own channel values, then what the utility they can achieve. So let's say node 1 does not know anything. So what it does, next slide please. What it does is it tries to allocate the equal energy equally in both the slots. Okay. So what it does is it does 2.5, 2.5 across both the slots, and but node 2 does, because it knows its own channel. So what it does is it allocates no energy in the first slot, and it allocates the entire energy in the second slot. So the total sum throughput you achieve is log 10, log 5 base 10 plus log 5 base 10, log 55 base 10. Okay. Next slide, please. Now, in a hypothetical scenario, had these both the nodes known that okay, this node is not going to transmit in the other slot, that first node had the first node known that the second node is not going to transmit in the first slot, it would allocate the entire energy in the first slot to avoid the interference. And the second node is anyway going to do what it was doing earlier. Then you can see that the overall throughput is better compared to the previous scenario. So it's a non-trivial problem because of its distributed nature. Okay, and even solving it in a centralized fashion in the large network scenario is quite challenging. So next slide, please. So we solve it using something called mean field reinforcement learning. So for that purpose, what we do is we use a tool called mean field games, which is essentially a construct from mathematical construct from statistical physics. What we do, what the mean fields games are, they actually have a large number of identical nodes, and each node, to be precise, we use discrete time mean field games, and each node can be in d finite possible states. D is finite here, so they can only be in finite possible states, and each node only knows its own current state and the fraction of the nodes in each state. So they know that what is the fraction of the nodes which has the empty battery, what is the fraction of nodes which has half full battery, what is the fraction of the nodes which has full battery. Okay, and at each time at a time each node uses the same policy. They just try to learn the policy, but since the nodes are symmetrical, we assume that they are so basically their learning processes are also symmetrical. And a node in state I takes action pi according to policy p. So this is the only variable they can control. Next slide, please. Okay, so whenever they take an action pi according to policy p, they get a reward. That is, the reward is same for all the nodes. That is the total number of successfully transmitted bits in the current slot. And they transits to some other state. That means the battery get depleted or the channel changes to some other slot according to some unknown probability pij pi. Okay, next slide, please. So the system basically so the evolution of the system can be actually captured by these two equations. So second equation here is, you can identify this is actually the Bellman equation, and this equation is basically kind of Kolmogorov equation for Markov chains, right? So basically what you are trying to say is that the fraction of the nodes in the n+1 slot those are in the jth state is equal to the fraction of the nodes in the nth slot in the ith state times the transition probabilities, and you just average it over all the i's. Okay, so to be precise, this is called Fokker-Planck equation, and it is the Bellman equation. So this is coming from transport theory. So how much mass is being transported? Anyways, just ignore that. So next slide, please. So so the solution of mean field games. So the mean field game is basically being described by these equations, and the solution of these equations, basically, if you take these equations from the discrete time to continuous time, these are coupled differential equations, and they are extremely hard to solve. Okay, if you know, even the differential equations themselves are very hard to solve, but on top of that, they are coupled differential equations, and they are, one is forward in time, another is backward in time. By what I mean is, you are defining, in one you are defining pi n plus 1 from pi n, in another you are defining bn from bn plus 1. Okay, so they are evolving in the opposite direction. They are coupled differential equations. So anyways, we have difference equations, so in discrete time. So the solution to these difference equations is a set of tuples which actually satisfies these equations. So which is a fixed point of these equations. So next slide, please. And a stationary solution is basically a fixed point of these equations. And we have actually shown through some analysis that this mean field game actually has a unique stationary solution because of certain properties of the utility function. Next slide, please. So let's ignore this proof, and next slide, please. In the interest of time. So now we know that there is a unique stationary solution of this mean field equation. That means these, if I somehow can reach to that stationary solution, which is the Ness equalizer of my system. Now the question arises, can we learn that stationary solution? And if I devise some procedure for learning that stationary solution, will it converge? And what will be the convergence speed? So my questions to those, my answers to these questions is, next slide, please. For a fixed pi n, we can devise a reinforcement learning based procedure to learn the optimal value, so that you can learn the stationary solution. Next slide, please. And we show that since mean field games has a fictitious play property, it will converge. And the convergence speed we actually show through simulations. Next slide, please. Next slide. Okay, so what we do is that at each node we learn, we use a reinforcement learning procedure to learn the optimal policy, and we use a fictitious play procedure. That is that we fix the distribution of the nodes across the states and try to learn the optimal policy using reinforcement learning for that fraction. Okay, and then once you take the actions using reinforcement learning, you again estimate the distribution pi under that optimal policy, and then you broadcast that pi so that each node knows the fraction of nodes in the states. And then we analytically showed that this procedure basically converges to the unique stationary solution. And the conclusion of this procedure, or to the summary of this procedure, is that nodes actually learn optimal power control policy in a completely distributed fashion. Next slide, please. So next, what we do is that we try to benchmark the performance of this policy against a centralized policy's performance. Had I solved this problem in a centralized fashion, then by solving in a distributed fashion, how much utility I can achieve if I solve it using this kind of procedure. So this column, the third column of this table, is basically showing the performance of our algorithm. So the network considered here is considering the 5 users, and each user has a 20 units of battery size. The 20 units of battery size, and the PDF of energy harvesting process is modeled as a truncated Gaussian distribution with the variance given by 3.5. And what we do in this experiment is we actually vary the mean of this process, and we try to learn the value for each mean value of this each value of mean for this Gaussian process. We try to learn the optimal policy, and what we observe is that the proposed mean field multi-agent reinforcement learning policy actually tries to achieves something like 95% of the centralized policy's utility. So it's quite good, right? While another policy, which is cooperative Q learning, which does not follow this kind of approach, just simply runs a Q learning at each node, reaches somewhere around 90% of this utility, or 92% on this. So next slide, please. So next result actually shows the convergence speed. So this is the time index, and what we show is that how the sum throughput of this network actually evolves. So you can just see that the sum throughput of this network just get stabilized within first 500 slots itself. So we are showing the simulations for two different mean values. So 99% of the optimum sum throughput is achieved for m equal to 7 within first 1000 slots, and for m equal to 5 it reaches 97% within 5000 slots. Next slide please. So the algorithm is quite fast, and these are some simulation parameters which we have used. So let's quickly move to the summary. Next slide please. Yeah, so we formulated this throughput maximization problem for EH feeding MAC as a mean field game, and we analytically showed that mean field game has a unique stationary solution. And we presented the mean field multi-agent reinforcement learning framework to obtain distributed policies. And the proposed policies achieve throughput close to state-of-the-art centralized policies. Next slide, please. So that brings me to the end of my talk, and these are some further readings. You can take a look at David Silver's lecture on YouTube, and there is Ras Salakuntadenob's lectures. This is the famous paper which proposed the deep learning, and the book on deep reinforcement learning by Sutton and Bartow is basically the Bible for this. A short book by Chajawas is a very good reading, only 100 pages on reinforcement learning. On multi-agent reinforcement learning, you can read this paper from our group. And on prioritized experience replay, you can read this paper by Tom Saul. And finally, some time for some caution. Deep reinforcement learning still doesn't work out of box. There are still some issues which are very well summarized on this blog post. So that's it. Thank you for listening to this talk, and I would like to thank Professor Kuntal for inviting me for presenting here. That's the end of my talk. I welcome if there is any question.
Yes, thank you, Dr. Mohit, for such a nice talk. We'd like to have some questions from the audience. We'll wait for 1 or 2 minutes.
Yeah. And I'm sorry for because it runs slightly over time.
No, it's perfectly fine actually. Exactly 1 p.m. No problem.
Thanks. Yeah, so in any case, if there are no questions, maybe you can, if there are any other.
So I have one couple of questions.
Yeah.
Like not questions. So since you are expert in this, so in this slide, I mean, these are the simulation parameters, right?
Yeah.
Like how do you, I mean, select this number of hidden layers or the number of neurons in first hidden layers? So an activation function, how do you fix this simulation parameters?
To be honest, there is no, still there is no formula for it. It's trial and error. So
okay.
You can say it's black art. You just run it.
Yes.
So initially I struggled a lot. I tried different architectures. So after that, I tried to do this to accomplish this task with the minimum number of neurons. So I just try to judge the complexity of the problem or the complexity of the function, and I try to shorten or enlarge my network so that my function approximation is my neural network is sufficient for approximating the function well. So that's the large guidance I had in the beginning. But now there are some guidelines emerging where they say that you should choose some type of architecture. Certain type of architectures are better, but mostly it is a black art.
Oh, yes, yeah. And these activation functions, Dr. Mohit, that there are so many activation functions. Like again, is it like a trial and error kind of thing, or like sigmoid, ReLU, and there are other activation functions, which one to select?
There are reasons to choose certain activation function in certain scenarios. So for example, in this work, this was my first work on reinforcement learning. I used ReLU, but then later on I realized that basically ReLU completely kills the gradient in the negative part. So then I tried leaky ReLU. That means you don't want the gradient in the negative portion to be too much, but you don't want to be zero if it is negative. So it's trial and error, but you can actually, based on your problem, if you analyze it, you can actually judge that what kind of function. And sigmoid is basically for probability distribution over the outputs, right? So in output layer you can use you use sigmoid, so sigmoid is more suitable for approximating the probability functions, right?
Yes, yes. Yeah, thank you, Dr. Mohit. There are a couple of questions, it seems.
Okay.
One question from Vijay Salwan. So the question is, why truncated Gaussian distribution is used?
Yeah, so because energy harvested can be only zero, it cannot be negative, right? So that is why we use truncated Gaussian. So
yes, the negative part is truncated. Yes. Okay.
Yes.
The next question is from Puli Anand. How much accurately does AI help to know the status of neighbor node battery level?
So it doesn't try to know, it doesn't care about the means it implicitly try to have some judgment about the status of neighbor nodes state, but it actually does not care directly. It just try to control its own actions. So it's not like a social activity, right? You try to judge what your neighbor is doing, what you know. You just do what is best for you, and that's it. You just have some estimate and you just try to do best according to that. You don't actually means, let's say in a scenario it's like humans, right? You can never know exactly that what everyone else is doing in a game, right? You just try to have some estimate and you just take your action. You don't need to very accurately know it. Why does consider feeding distribution? Oh.
Yeah, that's I think related to the previous question regarding truncated Gaussian. So perhaps.
Oh yeah, we considered a feeding distribution. It's not that it's a. Oh, you are saying that it's a Gaussian. We are considering a Mach Gaussian, right?
Mach Gaussian, not a physical layer, right?
No, it's a feeding channel. It's a feeding channel.
Feeding channel.
The feeding channel. We consider a feeding distribution, and I did not mention it on this slide because it is a standard called random relay distribution. It's not mentioned, but in actual work we actually simulated it using relay. We considered feeding distribution.
Yes. Okay.
Yeah.
Is there any other questions from the participants? Okay, so I assume that there are no other questions. So let us thank Dr. Mohit Sharma for such a nice talk and nice interaction with all the participants. So with this, we have the lunch break now. And we'll meet again at 2:30 for another talk by Professor Sudhan Maji from IISc Bangalore. So see you at 2:30 p.m. in the afternoon. Thank you all.